maybe I should take the.
Okay, thank you. And this is really a continuation of the first talk. And basically, we are moving from sorry, why it's so sensible? Sorry. Okay, from discrete random variables to continuous random variables. And basically, the title of the talk is a non-local Pearson diffusion. And this is again joint talk with Giacomo Affione and Enrico Pirozzi. And okay, so let's go further. So that's a plan of our talk: Pearson diffusions, Bernstein functions. Many things are already introduced by Giacomo. Then non-local Pearson diffusion, and again stationarity, correlation, what you call weak solutions, if you like, and so on. So the first is Pearson diffusions. Basically, let us consider two functions. One is linear one, a sub 0 plus a1x, and another one is quadratic one, d of x, which is d sub 0 plus d1x plus d2x squared. And sigma of x is square root of this quadratic function, well, some coefficient 2. And let us consider a stochastic differential equation in which with linear drift and diffusion of this special form in which diffusion is square root of quadratic function. And W of t is the standard Brownian motion. So ergodicity, we need some very weak conditions like mu of x of this form. For some u, sometimes it's called mean reversing diffusions. And again, diffusion space E for this diffusion is denoted by E. Yes, basically that's defined for those x for is d of x, which is quadratic term, is positive. And what is more interesting, why we call this Pearson equation, Pearson diffusions, the stationary probability density of the diffusion M of x satisfies so-called Pearson diffusion. So Pearson, by the way, it's very pleasant to name to use name Pearson because he was a student of King's College in Cambridge many years ago, of course, more than 100 years ago. And it seems he didn't work in Cambridge for a while, but basically he worked in London, King's College. So basically, more than 100 years ago, Carl Pearson introduced equation to unify all distributions which were known more or less used up to this time without any relation to diffusions. And for a density, he defined this is Pearson equation, m prime of x or m of x satisfies this equation. So again, here we have linear function in denominator. I use the same coefficients d, a, b, and what is more important, well, I mean in numerator. In denominator, we have a quadratic function. So, and basically, that's a famous Pearson equation from which we classified known up to his time densities, and there are Pearson time 1, 3, 4, whatever. But we will use another classification, as I will explain later on. But so far, we know all these Pearson type distributions which are not related to diffusion. And basically, there are 6 types of solutions. It's our classification, depending on degree of quadratic term. You remember that d of x is exactly what is denominator, and it's discriminant of this quadratic equation. Well, if of course this is really quadratic, degree is equal to 2. And this gives a classification of what we call Pearson diffusions from this point of view. So I will use standard notation, C sub 0 of E is a space of continuous function, and so on. Well, and there is a semigroup T of x, which is acting in this form, is a strongly uniform bounded C sub 0 semigroup of L2, and this is kind of standard material. And of course, for diffusion, we will use generator. And in this generator, again, we have a linear function and quadratic function. And well, we need some, of course, class of functions for which this generator is defined. And basically, the spectral equation for this generator is a hypergeometric equation. And again, this is well-known object because of basically classical orthogonal polynomials are polynomial solutions of hypergeometric equations. So that's why we have another very useful tool, classical orthogonal polynomials. And basically, the situation is a little bit more complicated if we compare the continuous distribution with discrete one, which was delivered by Giacomo. So in this case, for discrete case, we have kind of discrete spectrum. This is what you call spectrum category 1, when we have only discrete spectrum. However, it's also possible there is a spectral category 2, which is finite discrete spectrum and essential part of the spectrum. And they both separated by cutoff lambda. And also we have spectral category 3, which is finite discrete spectrum and essential part of the spectrum, or in probability there is a term continuous spectrum of multiplicity 2, separated by cutoff value lambda. So maybe I will. So like for a discrete, now lambda is not negative like was in the previous talk, but positive, let's say, because if you consider the minus generator, spectral equation for a minus generator, and basically that's a discrete spectrum. And now we have such a picture. There is a finite number of discrete eigenvalues, and also cutoff lambda, and then continuous part of the spectrum. For a spectral category 6, situation is even more complicated because we have here kind of two cutoffs, and basically lambda 1 and lambda 2, and then we have here minimum. Here is multiplicity 1, here is multiplicity 2, and again some sort of discrete part of the spectrum. Roughly speaking, it's of course not a definition, but that's the difference between discrete case and continuous case. And well, let me start with some examples. And the first is well known, Einstein-Beck process, a Gaussian stationary measure, and spectral equation is simply it has a linear eigenvalues, and eigenfunctions are Hermite polynomials. The next process is also well known, so-called Cox-Ingelson-Ross process. In this case, the stationary distribution is gamma, and instead of quadratic function, well, there is no quadratic function, just a constant. Instead of quadratic function, you have linear function, d2 is equal to 0, and basically Jacobi process in which we have full quadratic part, and d2 is negative, and stationary distribution is beta. So these processes are widely used in econometrics, in physics, in anomalous diffusion. Well, I mean, so far no anomalous diffusion, but basically there is also another cases when we call it Fisher-Snekker diffusion, in which we have full quadratic term here, d2 is not 0, and also discriminant is positive, and the stationary measure is Fisher-Snekker stationary measure, which we teach students in statistics, and also reciprocal gamma when we have full quadratic term, and again d2 is positive, but the discriminant is 0. And Gordic distribution is reciprocal gamma, so it's 1/gamma distribution. And most difficult is so-called student process, in which we have full quadratic diffusion, d2 is positive, and discriminant is negative, and stationary student measure here appeared. Okay, basically that's a summary, is that you have two non-heavy tailed stationary distributions, which is Pearson, all these Pearson, that's our classification. You have 6 Pearson distributions. One is Gaussian, gamma, and Jacobi, which are not heavy-tailed. And then you have a heavy-tailed part, which is Fisher-Snekker, 1/gamma, reciprocal gamma, and student. Okay, basically that's an eigenvalue problem for a generator, and we have here minus, so I use here minus in this place, but doesn't matter, of course, I mean. And in this case, for an Einstein-Beck process, you have linear eigenvalues, and orthogonal polynomials are Hermite polynomials. For a Cox-Ingersoll-Ross process, we have such a space for diffusion and linear, again, eigenvalues and Laguerre polynomials. And basically, for Jacobi process, we have a finite support, and eigenvalues are quadratic, and eigenfunctions are Jacobi polynomials. That's a well-known processes which are well studied in probability and other areas. So we consider L2 space, which is normal, I mean, with weights, which is came from the stationary distribution, like Gaussian or gamma, whatever. And eigenfunctions, of course, consist of a basis of this L2 space, and basically the transition density can be written in this form. Again, as Giacomo already explained, we would like to express, if you consider, I mean, in no local sense, we would like to replace this exponent into something like Niederglasser function or even more complicated function, which was already introduced, by the way, in the first talk. And these polynomials are simply either Hermite or Jacobi or Laguerre in the case when we have infinite, when we have a spectral category 1, just infinite number of eigen values. Okay, spectral category 2. In this case, you have such a quadratic form of d of x quadratic function, and well, some parameters, which are parameters of distribution, of course. And again, we have a space of diffusion of this form, and lambda and eigenvalues are quadratic, and polynomials are given by Pearson-Decker polynomials. Well, they exist under some cutoff, which is now, do we have here cutoff? Something like something this one. Okay, that's basically. No, a little bit. Yes, that's a. We have finite number of. This is orthogonal polynomials, which so many orthogonal polynomials, so many moments. That is why basically we have a finite system of orthogonal polynomials. Okay, and this is the cutoff. Sorry, that's not yes, and cutoff is of this form. Lambda is this form, and we have well, essential part of the spectrum in this case. And again, this essential part of the spectrum is not easy, but however, explicit can be explicitly expressed in terms of some special function solutions of the Sturm-Liouville problem for this case because of. The next case is reciprocal gamma polynomials. So basically, these polynomials we called it Pearson-Decker, and they were missed in the classical book of Söge, and basically. He mentioned only two systems, but in fact, through this classification, we can see there is one more, which is called, we call them Pearson-Decker because of station distribution. This is Pearson-Decker, but however, well, that's our name. Anyway, if you have a quadratic function of this form for a d of x, then eigenvalues are quadratic, and eigenfunctions called Bessel polynomials. For this, they are well known. There are books about Bessel polynomials. And again, we have this type of picture. And that's a spectrum. Cutoff is of this form, depending on the parameter of the Pearson-Decker polynomials. And again, the functions from essential part of the spectrum complicated back explicit again. Okay, and basically for a continuous time distribution, we have such a picture. There is a kind of orthogonal polynomials, and here is stationary measure, and we have finite number of such terms. But also there is another part, which is an essential part of the spectrum, in which we have again kind of spectral representation, but with another this continuous part, like I decided here. And finally, the most complicated case is, for our point of view, is student case. We have a quadratic term of this, well, under square root of diffusions, and basically the student distribution could be skew or not skew. There are some conditions for this, and eigenvalues are quadratic, and functions are, we called it generalized Roth-Romanovsky polynomials. Actually, it's again interesting story that Romanovsky wrote only 2-page paper about this with kind of many partial cases, but it was like beginning of 191. I mean, the date is 195 or something. And then we have found the paper of some person which is called Prof from Cambridge, by the way, in physical journals, 30 pages with full description of this polynomial. So it's strange that this was kind of missed historical information. Then we use the name, we add, that's our suggestion to add to the name Romanovsky also, the name of this. And basically we have found this paper in the library of the Cambridge University. Absolutely forgotten paper by this. Okay, anyway, let's go further because we are a little bit out of time. And again, we have cutoff, but this cutoff, of course, is a different nature. The minimum of 2 cutoffs. We have some sort of more complicated spectral structure, but anyway, we have a structure, spectral structure. And of course, we have again this discrete part of the spectrum and essential part of the spectrum. And as you see, the essential part of the spectrum is more complicated. This means that we have multiplicity 2 in some area for this spectral problem. Okay, so I'm a little bit slowly, but again, the second part is what's already introduced in the previous talk and more or less identical. So maybe I will be very fast here. So we have a function is said to be completely monotone if we have such a property. Also, it was mentioned by Louisa and many others in this talk, Kolkoltsev, and also the function is Bernstein function if you have such a property. So I will be very fast because it's already mentioned, I think 5 or 6 times. Giacomo mentioned 6 times, so it's he was a 7th, now 8 times we use these definitions. And again, we have Levi-Hinchian representation only to introduce notations that mu phi is still Levi measure, and basically we have a triplet of each defined uniquely as a Bernstein function. And again, notation still the same as in Giacomo talk. We have phi of lambda, and again, this Levi measure is associated to lambda, and well, important that we have the function is called conjugate to this function, and if this conjugate belongs to Bernstein function class, is said to be a special Bernstein function, and we have this type of phase. And again, this definition of complete Bernstein function, I think in this audience it's known. I will the importance that we have here some measure, Levi measure, and there is a relation between these 2 classes, Bernstein function, complete Bernstein function, and so on. And yes, and basically important that we will use this measure nu bar, which is Levi measure from t to infinity in the definition of the well, subordinator is non-negative and increasing Levi process sigma of t. And of course, Levi Laplace exponent subordinator is given in this form. And this is the same function phi, which is Bernstein function. And so, I mean, this notation typical for this conference, and this is inverse subordinator finally. For any subordinator, we can define first passage time process, which is called inverse subordinator. So I will be very quick here because of this is well known. And again, important that we have here this notation. And by the way, there is a density of a Levi process, and the known Laplace density of this, so Laplace transform of this density in T is defined by this formula. I think I already mentioned 5 times in this. And then basically, given a Markov process, which is non-local Pearson diffusion and inverse subordinator, we can define semi-Markov process as superposition of 2 independent objects, as already many people did in this audience and in this conference, and but just to introduce notation. So again, this is not inverse subordinator, which is related to function phi, which is Laplace exponent. And basically, we have a non-local derivative, which is called sometimes Caputo type, because of here the measure is already introduced, defined by Levi measure from t to infinity. And again, this is a function. This is regularization because of this written as a Riemann-Liouville derivative, but because of this term, it's actually Caputo derivative. Because of Caputo is simply a regularization of Riemann-Liouville again, and the same as was in the previous talk. And you know the history of this definition. Actually, Professor Igor Podlubny told us that even in Caputo original version, it was already introduced this object. But of course, the probabilistic sense was emphasized by Kochubey and Toalda. And again, the and the classical case is well, that's the same. This is Caputo form of derivative. We have derivative under the integral, and the classical case when phi of lambda is lambda to the power alpha, and we have a alpha stable subordinator and inverse to it, and well, that's a classical Caputo fractional derivative. Again, well, this is we have to use a time change semigroup, and which is already introduced in the talk of Professor Kolotso at the beginning of the conference. And again, if this is case which is kind of main case which we have to compare our results and find the density of the, and well, this is not a semigroup, but okay. Again, similar to, so let me formulate our results basically, because there's too many notations from different areas. And but again, for any function which is completely monotone, it means that for any subordinator is Laplace exponent 5. Then the function which is defined in this way, which is one parameter of linear operator from one multiplied to another, is a strong solution of this of this Cauchy problem, in which in the left hand side there is this derivative of which is related to the function phi, sometimes computer, sometimes more general than computer. In the right hand side there is a generator of our process, and yes, I'm really a little bit of time. Yes, again, important that as Giacomo already explained, that for this eigenvalue problem, the solution is also known, and this is basically a moment generating function of this L phi of t process already from the previous talk. And for instance, if you have a stable subordinator, this is simply Mittag-Leffler function. So we can think about Mittag-Leffler function of e to the power alpha of minus t to the power alpha, lambda t to the power alpha for the classical case. And again, we use this estimate, which was already used in the previous talks. And so basically, that's our definition of non-local Pearson diffusion. So we have a classical Markovian diffusion, and then we substitute inverse subordinator of general form L phi of t, which is not necessarily alpha stable, but more general form. And it means that we have to consider such a stochastic, that's a unique strong solution of such a stochastic differential equation. In time is changed into the inverse subordinator, and here is again time is changed into inverse subordinator. Such an object, and we have to the solution of this. So we can use either language, but in this kind of a little bit not trivial form. And instead of the process is not Markovian, we can use what we call transition density. Basically, this tradition came from the physical papers to use transition density terminology for a non-Markovian case. And so, and again, we can write this using conditioning. We can write distribution of this process because of its simply conditioning. That could be like density of inverse Gaussian, inverse alpha stable subordinate, but in general something more general. And again, in the case of non-local Pearson diffusion of spectral category 1, when we have such a spectrum, this what you call transition density for non-Markovian case can be written in this form, and you can recognize the same form as we also already used. Orthogonal polynomials, either Hermite or Laguerre-on-Jacobi stationary measure, and here is a function which is could be exponent for a non-local diffusion, and e to the power minus lambda Mittag-Leffler function for a alpha stable subordinator, and it is inverse, and more general function which was already defined. So which is kind of expected result. Well, let me omit sketch of the proofs. Again, the spectral decomposition of this what we call transition densities again contains for spectral category 2 the same structure, but again we have a finite system of orthogonal polynomials, either Fischer-Steindecker or Romanovsky, or Bessel polynomials, because of this still spectral category 2, and some essential part of the spectrum is the same function, but again here we have this function which is either exponent for local case or Mittag-Leffler for alpha stable or something more general which was defined. I think I have still 5 minutes because of I started later. Yes.
You're right, but there's also question. So 5 minutes including question.
Including question. So I'll try to formulate now main results. And for spectral category 3, we have a similar representation, but again we have a finite number of eigen functions and eigenvalues, which are Ross-Romanovsky polynomials. And again, because of this is spectral category 3, we have more complicated essential part of the spectrum. So the first result is we can write down explicitly all spectral representation of the spectral densities in this what we call non-local Pearson diffusions for spectral categories 1, 2, and 3. Okay, let me omit the sketch of the proofs. So mainly here's, well, okay, and then the next step, exactly in the previous talk, we have to consider the Cauchy problem with either generator of the Markov process or with Fokker-Planck equation, which is Fokker-Planck equation. And the difference is now in the left-hand side we have this non-local derivative, and there is initial conditions, and basically we have a solution of this Cauchy problem, and basically again the result depends on the spectral category, but they are kind of expected because of in all cases we have a solution of this form if initial condition can be expanded in the some series. This is spectral category 1 when we have an infinite number of eigenfunctions. If this is L2 with weight expansion like Hermite or Laguerre or Jacobi, and GM coefficients here, and basically that's the solution of this problem. Again, that's orthogonal polynomials, coefficients of initial data, and this function which are either exponent or Mitter-Claffer or more general. And the same for a Fokker-Planck operator. When we have Fokker-Planck equation with left-hand side, which is non-local operator, we have such a solutions. And well, for a spectral category 2 and 3, results are again expected, but of course, based on the spectral decomposition I already mentioned, because of instead of this infinite sum, we have a discrete part of the spectrum and essential part of the spectrum of different type of a different type of depending on the spectral categories. And finally, just 1 minute about, so we can see what we call the and the process is simply time change process. We have a Pearson diffusion and we change time by independent inverse subordinator. What is the property of this stochastic process? Okay, we can deliver a clear form of exact distribution, which is basically in the limit the same as Pearson class of distributions. And we can deliver a covariance function of this form. So you can recognize again the same structure as was mentioned by Giacomo with the same functions. And surprisingly, we have very many similarities between the discrete case and continuous. Well, with discrete distributions, which are in Giacomo case, they have only discrete spectrum. It was whatever Poisson, a negative binomial, and some other ergodic distribution of both these processes. And here we have a 6 type of distributions. It's much more complicated structure of the spectrum of the generator. Okay, that's all because I think I have to stop. Thank you for your attention. And I brought one collection of the, well, also I did this research not only with Giacomo and with Enrica, but also with Mark Meerschart. It was our first paper, and with other people from Croatia, my former PhD students. So the basic papers are here for those interesting, just 5 basic papers, because of general there are more than 10 papers on this topic. Okay, thanks.
Thank you very much. Yes, please, maybe 1 or 2 questions. Yes, go ahead.
Thank you very much. It was very interesting talk. I wanted to ask a question about when you wrote the equation for the subordinated process. So you said you have X satisfied some RCE.
Yeah. Yes, yes.
And so is it kind of a general result, or is it particular result for this?
Well, it's quite a general. There are basically the key paper is a paper of Kobayashi from New York, I suppose. It was his PhD topic when he defined such an object. Like we have a very general subordinate, even on Markovian. Any process which is increasing kind of subordinate you can use, not even Levy type. And he defines these objects. I can send you his dissertation, actually, PhD dissertation. I don't remember who is supervisor. But of course, we applied this methodology to our case, which is quite specific.
Thank you. I have a remark. In physics, we look at the correlation functions, especially when for the choice of the Mitter-Claffer case, not in generality. And then these correlation functions depend on the ratio of the 2 times. And I think this is a nicer representation in the sense that you can have a ratio of 2 functions and the 2 times T and S. and find out what exactly is the correlation function in that way, because this is a more general representation, but
Yes, yes,
I
actually.
think it hides what we call aging. So this is just a remark.
Yes, thank you. Actually, this I think we have, well, actually this proof is basically new, and well, this proof is not new because we used the proof from my previous talk with Meyer-Sharp, work with Meyer-Sharp. And actually this paper in which we have found this way of kind of integration by part for a function of two variables is non-trivial, and many people citate it and use this method. So, but I think I have here, or maybe not, but anyway, I can send it.
We can talk later. Thank you very much. Thank you very much. Nice, very nice talk. The personal talks are much more enjoyable, I have to say.
Yes, you are absolutely right.
Okay, but now we have another virtual talk. Thank you. Okay.